going on here. So this is the talk that I gave at the Chesapeake section meeting of the American Association of Physics Teachers. Um, it was at the end of October, so not quite a month ago. Jason was there, but it was supposed to be recorded, but they never actually recorded it. They had a lot of technical issues at this meeting, which is unfortunate. So I don't have a video of it to show, but for you guys, I can just show it right here. Um, so uh, the main idea of the talk is to discuss what happened in 1925. I mean, I think everyone knows that matrix mechanics was invented in 1925, but very few people know what it actually is. Um, so does anyone, I'll just ask that question of this group. Aside from Jason, does anyone actually know how original matrix mechanics worked? And that's what I thought. So it all started in the summer of 1925, and three critical papers came out. The first one was by Heisenberg, über quantentheoretische Undeutung kinematischer und mechanischer Beziehungen. It's something like on the theoretical quantum relations, kinematic relations, and mechanical. I forget what I think it's redefinition is what Beziehungen means. Um, Essentially, what Heisenberg was saying is, uh, I have a new way of thinking about what quantum mechanics is. And then very shortly after Heisenberg's paper, Born and Jordan really properly formalized what quantum mechanics is. And they had the incredibly clever title On Quantum Mechanics. And then just a couple of months later, uh, the three of them got together to write a paper. This one is called On Quantum Mechanics 2. It's usually called the three-person paper or Dreimann-Arbeit in German. So you might see that mentioned somewhere if you look into the history. It's actually quite interesting to look at things, especially this third paper. Um, and if I think all of these papers are translated into English, you can find translations into English. But there, I think there's also a Phys Rev article that Born wrote that kind of summarized all of this in English at around this time, like maybe 1926. But there also is, Born gave a series of lectures at MIT, and that is a book written in English, and all of the ideas are in there. And it's very well written, very easy to understand, and I highly recommend if you have any interest in looking at this any further to take a look there. So I'm actually not going to talk about the history of exactly how this was discovered. Tons upon tons of people have done this. Not all of them get it correct, but most of them are pretty good about what was going on. And the reason why is this was done in a context where it was believed that Bohr-Sommerfeld quantization was sort of the right way to do quantum mechanics, but it needed some tweaking. And all of the thinking that went into determining how matrix mechanics was discovered was within that context. But that's like the totally incorrect context to think about quantum mechanics today, because we're not believers that the Bohr-Sommerfeld quantization condition is somehow fundamental in some sense. So what I'm going to do is tell you the story in a sort of modern way where everything fits together and can be done in sort of a modern light. So I'm going to show you both the art and beauty of how matrix mechanics works. So to set the context, Bohr and Sommerfeld had a series of rules, and if you had periodic motion, you would integrate the action around one period and set it equal to an integer multiplied by, that's actually a typo, it would be multiplied by h. And this actually produced the correct relativistic energy levels of hydrogen. So this is hydrogen plus the fine structure, which is truly remarkable. I mean, it's truly remarkable that Sommerfeld was able to actually integrate the relativistic equations of motion for hydrogen, quantize them, and verify that he gets the energy levels completely perfect. But it fails in almost every other situation. As I said, they don't get harmonic oscillator correct. They get hydrogen correct. That's really the only thing that this approach actually gets correct. But they had incredibly accurate spectra. So they had this really frustrating situation where they have a theory that somehow must be doing something right because it gets these answers to incredibly high precision correct for hydrogen, and yet somehow must also be wrong because they can't make it work for everything. So this is a very frustrating time, period of about 10, 15 years between the time when Bohr put out his theory and when matrix mechanics was discovered. Now, the old quantum theory was based on some ideas of Ehrenfest on adiabatic invariance. And if you think about this, this is in many respects a natural thing. Quantizing the action sounds like a completely made up ad hoc thing that you might do. But you can actually translate that instead into quantizing adiabatic invariance of classical motion. And an adiabatic invariant is something that is robust to change. It doesn't change when you slowly change parameters in the system. So the classic example of this is a pendulum where you slowly change the length of the string of the pendulum. But a more important example is a harmonic oscillator where you slowly change the frequency of the harmonic oscillator. So as you change the frequency of the harmonic oscillator, the energy changes. But if you change it so slowly that the frequency looks approximately constant over, say, a couple of periods of motion of the harmonic oscillator, then what you find, the ratio of the energy to the frequency is an adiabatic invariant. And that actually doesn't change. Even if the frequency changes by a factor of 2 or 3, E over omega remains constant. And so what they would do following this adiabatic invariant way of thinking is you would say the adiabatic invariant is the robust quantum object. So that's the thing we quantize. We set it equal to n times h bar. And then what you see is the energy of the harmonic oscillator, E would equal nh bar omega, which is not correct. But that was what they thought the quantization condition is. It got the energy level spacing correct, but it didn't get the ground state energy correct, because this would predict that the ground state energy would be 0 rather than 1/2 h bar omega. Okay, and so the way that I describe that is it gets the leading values for quantization correct. It gets the leading values correct, but does not capture the quantum corrections, which is the plus 1/2. And the reason why hydrogen works so well is there are no quantum corrections. The energies are just functions of n. It's not n plus a half or n plus a quarter or n plus some number that's, slowly changes. It's just n. And that's why it works perfectly for hydrogen. Okay. So one of the things that you would arise if you were thinking about periodic motion classically is we know periodic motion can be expanded in terms of the fundamental frequency and the harmonics. That's what a Fourier series tells you. So you would expect the motion to involve the fundamental and the harmonics. When we look at spectra, it doesn't look that way. You don't find spectra that are coming out at some fundamental frequency and then multiples of that frequency. Instead, the spectra can be shown to be described in terms of energy differences. And this principle is called the Rydberg-Ritz combination principle. And this is sort of a fundamental property of quantum mechanics that you have to incorporate into some description of quantum mechanics. And this was the thing that Heisenberg was sort of grappling with. Heisenberg described it as we should only look at observables. So we shouldn't think about trying to find the orbit of an electron about an atom because we can't observe that, but we observe the frequencies. So our theory should focus on the frequencies of the system, okay? So his solution, and I think if any of us thought about this for a while, it's in many respects the only solution, is to use matrices that incorporate that dependence on the difference in energies. And the other thing you should keep in mind is classically when a charge oscillates in a periodic motion, that will radiate energy. So one way of thinking about these quantum jumps that Bohr postulated is that the way that you get the quantum jump is that the quantum mechanical system is oscillating at the frequency difference, and that of the energy states, and that then eventually creates this photon that radiates out, and you have a transition. So you want things to depend harmonically on the energy difference. So we say we have these matrices that are numbers multiplied by this harmonic time dependence. And this is essentially the postulate that Heisenberg came out. So we'll have one for position, we'll have one for momentum. That frequency difference is the difference in energies divided by h bar. Okay. H bar comes in because I want to convert from an energy to a frequency. All right. And the main thing that convinced Heisenberg that what he was doing is correct is if I calculate q squared mn, and I use just matrix multiplication to calculate q squared mn, you will find the frequency factor of q squared is also e to the I omega mn t. And that means if I construct any function out of p's or q's, they also will have this exact same time dependence. So it sort of solves the problem of how do I get this time dependence that depends on a difference of energies robustly into the system. And matrices automatically do that. And that is sort of the key observation. He also observed, even though he didn't know that these were called matrices, he called them tableaux. And even though he didn't know that these were, he didn't even know matrix multiplication. He invented matrix multiplication in order to have the q squared have the same time dependence as the q. He did recognize that if he took the product of two matrices, q times p, and looked at the product in the opposite order, p times q, they most likely were different. And so that motivated looking at the commutator qp minus pq because it's not zero. Okay? So one of the first things that you get from this, now you have lots of people who will say that, you know, you can't derive the Schrodinger equation. Once you have made this assumption, which is a reasonable assumption to make, you can derive Schrodinger equation. So here we'll derive it. In this form, it's called the Heisenberg equation of motion. But if you think about it, this is actually the Schrodinger equation. We're going to take the time derivative of that matrix. Because it has this exponential factor, the time derivative is trivial. It brings out an e to the I omega mn that multiplies q. I'm going to re-express it in terms of the energies. And now I'm going to use something that is very important. My Hamiltonian doesn't depend on time. There's going to be a Hamiltonian matrix because everything is described by a matrix. But the Hamiltonian is time independent because Hamiltonians of most systems that we care about are time independent. That means the Hamiltonian is diagonal in this basis because the only matrices that are time independent are ones that are only non-zero when m equals n, because then this factor goes to equal 1. So the H is diagonal, and it's pretty obvious I should put the energy levels as those diagonal matrix elements of the Hamiltonian. So when I think in terms of matrix multiplication, this is actually the commutator of H with Q, the Mn matrix element of the commutator of H with Q. So we get Q dot is I over H bar commutator of H with Q, which is the Heisenberg equation of motion. And it just comes out of assuming this matrix form, which I think is pretty cool. The next thing that we can show is that this canonical commutation relation is a constant of the motion. And the second element that Heisenberg brought in is that these objects that are matrices, that he's not really sure what he's going to do with them, they will satisfy the same classical equations of motion as we have in classical mechanics. And in many respects, you can think of this as an application of the correspondence principle. However, I'm using these matrices. Eventually, they have to describe classical motion. So I should have these quantum matrices satisfy the same equations of motion as the classical equations of motions. That means Q dot should be 1 over m times p, and p dot should be the force, which is minus dv of q dq. Now, you might be concerned, how do I take a derivative of a potential with respect to Q? I think the best way of doing this is really thinking of this as f of Q expressed now as a function of the matrices rather than scalar parameters. And what that means is you actually take this derivative with respect to the scalar parameters, find out what the function is, and then replace Q by the matrix in the functional form. And that would be the way in which you would do it. All right, but we're going to now use these classical equations of motion, and these classical equations of motion are the Ehrenfest theorem. And so essentially, one way of thinking about doing quantum mechanics or doing postulates for quantum mechanics is to postulate the matrices in order to have the Rydberg-Ritz combination principle, postulate classical equations of motion because of the correspondence principle, and you want this to somehow connect to the classical mechanics that we know is correct in the classical limit, and then look at what the consequences are. So now we're going to look at what are the consequences on the canonical commutation relation. So let's look at the time dependence of the canonical commutation relation. We can take the derivative of it. It just distributes across the two factors. So I get Q dot commutator with P and Q commutator with P dot. Now, if I use these equations of motion, I can replace Q dot by P over M, but of course, P commutes with P because it's just P squared minus P squared. And I can replace the P dot by minus dV of Q dQ, but Q commutes with any function of Q because I can rewrite the function of Q in a power series in Q, and then when I multiply Q from the right or from the left, it's the same thing. So the terms will all cancel and I get 0. So we get from this that the time dependence of this commutator QP is 0. It's a constant, okay? We're now going to take this and we're going to use the Heisenberg equation of motion, which replaces d by dt by a commutator with h. So it's also equal to I over h bar commutator of h with QP. But H is a diagonal matrix, so I can just write that out as EM minus EN times QP MN matrix element. Now, if I'm working with a non-degenerate system, so the only time EM equals EN is when M equals N, what we learn from this is that the matrix QP is equal to 0 when M doesn't equal N. So QP is a diagonal matrix. So we will write QP is some diagonal element CM times delta MN. All right, everyone with me on this? Okay, now the final part of the derivation is to look at P is equal to MQ dot, use the Heisenberg equation of motion for Q dot. That makes us take the commutator with H, rewrite H as P squared over 2M plus V of Q. Again, Q commutes with V of Q. P squared with Q you can work out using the Leibniz relation for commutators, which is very easy to derive. It's P QP plus QPP. And now we can plug in the fact that QP is a diagonal matrix with the diagonal matrix element CM, and use the fact that, let's see, I'm going to also multiply by IH bar on both sides. So what this equation says is IH bar PMN is equal to 1/2 CM plus CN PMN. So again, that's a rigorous equation. Now, this is solved by CM equals IH bar, which would say that the canonical commutation relation is IH bar times the identity matrix. But there could be other solutions of this as well. For example, if PMN is only non-zero when M is even and N is odd, I could pick CM equals 2IH bar and CN equals 0, and this would work as well. Okay? You need to bring in another postulate at this point in order to solve the equation. And that other postulate is that the canonical commutation relation does not depend on the Hamiltonian. And the way to understand why this should be true is if we take Dirac's perspective that the canonical commutation relation is related to the Poisson bracket. The Poisson bracket in classical mechanics does not depend on what Hamiltonian it is that you're solving. It's always equal to 1. And so if we make this another postulate that the canonical commutation relation does not depend on the Hamiltonian, what we know if we go from one energy eigenvalue solution to another energy eigenvalue solution, because we've changed the Hamiltonian, that will correspond to a basis change. So we'd have to take whatever the canonical commutation relation was in our current basis and do a basis change transformation onto it. Well, the only matrix that's invariant under all basis changes is the identity matrix. And so this requirement that it doesn't depend on the Hamiltonian is the same as saying it must be proportional to the identity matrix. And then what you find is CM is equal to IH bar. Okay? Everyone clear with that? It's a little bit of a subtle argument, but everyone clear on how that works? All right. So we have derived this. And I really want to say we have derived this from the postulates. So the way to think of this is we motivate a matrix representation from the Rydberg-Ritz combination principle from spectra. So we experimentally motivate the use of matrices from spectra. We then postulate the Ehrenfest equations of motion and that the Hamiltonian is diagonal in the basis that we're working in. And then finally, the fourth postulate is that this canonical commutation relation is independent of the Hamiltonian. And then you can derive this. So even though many textbooks say you can't derive this, I've just shown you can derive this. But the catch is, in most textbooks, they postulate this and then they derive the Ehrenfest theorem. Instead, what we did was we postulate the Ehrenfest theorem and we derive the canonical commutation relation. I actually think that order is a much better order for how we do this because it is it's a more natural way of thinking that the postulate is that the equation of motion should be the same as what we have in classical mechanics. Okay, now P is equal to mq dot, and we can rewrite q dot in terms of omega mn. So let's look at commutator of q with p, where I'm going to replace p by I m omega mn times q. Then because the p multiplies on both sides and I'm taking a difference, what we get is I m sum over m prime omega m prime n minus omega m prime q m prime q m prime n. Let me derive the first one for you so that you're clear on how that works. That's where q is first and p is second. So the q is m prime. Then I introduce the p, which is omega m prime n q m prime n. You see? And then the other term is what you get if you introduce it in the opposite order. All right, but we know what this is. It's IH bar delta Mn. All right, so now we're going to use two facts. One, the Q is a Hermitian operator, and the way that Heisenberg essentially postulated this as well, because from his perspective, he only knows the upper triangular part of the matrix due to spectroscopy, and he just postulates the lower part has to be this, has to be the complex conjugate with the M and the N inverted. And so that's just that was just a postulate that he came up with in his paper. We, of course, know the Q matrix must be Hermitian. So again, you can think of this as a postulate if you like, but once you take the Q matrix as Hermitian, and we pick M equals N, you see I will have here Q N M prime, Q M prime N. That's the absolute value of Q M M prime modulus squared. And it's multiplied by omega MM prime. And I'm going to just divide by IM, okay? And I get two of these factors from these two terms. They're exactly the same and they add together. So that's where the 2 comes from. And the minus sign comes from the fact that we actually have picked this term because it's omega MM prime, which has a minus sign on it. So you get this relationship, omega MM prime Q MM prime squared equals minus H bar over 2M. This is another way of writing the canonical commutation relation, although it does not look like that, okay? All right, now we're going to solve the harmonic oscillator. So harmonic oscillator is H is P squared over 2M plus 1/2 M omega squared Q squared. We can rewrite the classical equation of motion, second derivative with respect to time of Q, which will give me an omega Mn squared, minus omega squared times QMN is equal to 0. That's the classical equation of motion. So now, when QMN is not equal to 0, I must have omega squared Mn equals omega squared, which means omega Mn is plus or minus omega. That's the only situation where QMN can be non-zero. We're going to now consider the lowest energy state. We're going to label it 0. Because there's no state lower than that, we can only have omega 0,1 to be non-zero. There's no state -1 that this can connect to. In other words, there's no energy less than it. So the minus, I guess the plus omega does not work. All right, so we now learn that omega 0,1 is actually equal to minus omega, and only Q01 is non-zero. All right, so now if I come back to the previous relation and I recognize that M is 0 and only M prime equals 1 is non-zero, this is one term. So I can solve for this guy. So we learned Q01 squared is minus H bar over 2M omega 0,1. Don't let the minus sign fool you. Omega 0,1 is negative, so we can rewrite that as H bar over 2M omega. All right? Now, we can compute H00. We just take the 0, 0 matrix element of this. It is equal to M squared omega 0,1 squared over 2M plus 1/2 M omega squared modulus Q01 squared. That is what H00 is. Okay? And we can simplify that. That's just M omega squared Q01 squared. Plugging in what Q01 squared is, we get 1/2 H bar omega. The correct ground state energy. Now we get all the rest of them simply because omega Mn steps up by omega. So all the energies are just integer increases by omega, or H bar omega. So we immediately find En is H bar omega N plus 1/2. That's it. That's how easy it is. Okay? So, when you work in matrix mechanics, you calculate the spectra without determining the eigenstates or the wave functions. Okay? No differential equations, nothing like that. Personally, I think it's really beautiful how this all fits together and how everything works. All right, so it's a pity that you can only solve the harmonic oscillator and orbital angular momentum problems this way. And that's kind of it. That's all that I wanted to say. Both Leanne and Jason are working with me on the project. And I guess the only thing I want to reiterate is if you want to teach quantum mechanics in a postulate way, which is very common in textbooks, they list quantum postulates. What this is saying is an interesting alternative set of postulates that you could consider is quantum objects are described in terms of matrices that have this harmonic time dependence. That is then consistent with the Rydberg-Ritz correspondence principle. I'm sorry, combination principle. You say that those matrices must obey the Heisenberg equation of motion. That's essentially the correspondence principle that says I have to get the same result in the classical limit, even though I don't really know at this stage how to get to the classical limit from these matrices. The next thing that you say is that because the Hamiltonian is time independent for the problems I'm interested in solving, the Hamiltonian matrix is diagonal. And the fourth one is that the canonical commutation relation is independent of the Hamiltonian. And with that, you derive the canonical commutation relation, that it's IH part. It doesn't have to be a postulate anymore. And you can solve the harmonic oscillator problem essentially immediately. Very straightforward to directly solve the harmonic oscillator problem. Okay, so I think it's pretty cool. I mean, I think that this is a really interesting story, and it's an interesting sort of bit of mathematics that I think everyone who learns quantum mechanics should see. I think it actually makes a lot more sense about where quantum mechanics comes from. So how would you complete the postulates? Well, the next thing you would have to do, because we can't just work with the matrices, the next thing you have to do is you have to say, the matrices actually tell us about some additional abstract structure that we have to work with. And to work with that abstract structure, we have to introduce states that are vectors in some space. You might want to call it a Hilbert space. If you want to be more correct, you might want to call it a rigged Hilbert space. And we have operators that act on this space, abstract operators that map vectors into vectors. And these matrix elements are just the bra state operator ket state sandwich that are a set of numbers. And if I work with an energy eigenstate basis, so I work with states that H acting on N is equal to En acting on N, and I work in the time-dependent states so that the states have a phase factor e to the minus I En over H bar times T in them, you get the Heisenberg matrix immediately that comes out. And so you can connect, you can even sort of say that, you know, working directly with the matrices is too difficult to solve the general problems. So we have to expand our abstraction to talk about states in a space whose matrix elements are these matrices. And, you know, with two more postulates about the states and the operators that act on the states, you then have everything. You then would just need, in addition, the Born rule. And then you have essentially all the postulates you need to sort of discuss quantum mechanics. And again, it kind of strikes me that this way of thinking about the postulates for quantum mechanics is just a really cool way of sort of doing stuff. So, um, so in any case, I wanted to share that with you. I think it's a really nice idea. I'm curious what you guys think, whether you like it or not.
I have quick questions. I think it's on the first few slide where you can isolate it, the Q and M, into whether it's basis dependent part and the phases where it's time dependent part. Um, is it just coming from the fact that the Hamiltonian is time independence, or how should I justify that solid to do that?
Okay, so again, the way the logic goes for Heisenberg is that um, if I have these objects that we know are matrices, and I use matrix multiplication as the rule, then if I say Q and P have this time dependence, e to the I omega mn times T, then I'm guaranteed that any function of Q or function of P will also have that time dependence. So any object that I want to construct from these matrices will also have that time dependence. And this is the way that he envisioned you must invoke this postulate in order to be able to be consistent with the Rydberg-Ritz combination principle. Now, this doesn't show you how you derive the Rydberg-Ritz combination principle from it, okay? But the thinking is that whatever it is I'm working with, Rydberg-Ritz tells me it must depend on the energy differences. And in terms of objects that you can work with, this is the simplest object that you can work with that naturally incorporates the energy differences so that everything in your theory has those same energy differences in its dependence. Okay. It might, I'm not a mathematician, so it might be uniquely the only thing that you can construct that does this. But it certainly is the simplest thing you can construct. Yeah, I mean, you have to have something that depends on two indices. Otherwise, you can't do anything with it. So it has to depend on two indices. And it's very natural how the matrix multiplication makes it so that this works in, for all objects. All objects will have the exact same time dependence. So that's sort of the key. That's why you stick with the matrices. That's why you stick with, okay, I have these matrices. What do they mean? And I have no answer for you at this stage. And Heisenberg had no answer, and Born had no answer, and Jordan had no answer. They didn't know, but they found that using them, they could solve problems. So this was really cool. And they actually had some ideas about how you could sort of construct the matrices in some other basis and then potentially diagonalize them. But of course, we have no algorithm that can diagonalize infinite dimensional matrices. So we don't really immediately know how to solve other problems. And they struggled like everything to try to solve hydrogen. They eventually begged Pauli to try to solve hydrogen. And Pauli solved hydrogen. But he didn't solve it by finding the matrices of H for hydrogen. He solved them by using conservation of angular momentum and the fact that there's this thing called the Runge lens vector that is conserved in orbital mechanics, because the hydrogen problem is the same as the gravitational problem. So he used the conserved vectors. He found a set of operators. He actually discovered the algebra of SO4. And by working with the algebra of the operators of SO4, you can get all the energy eigenvalues of hydrogen. Now, you see, they knew what the answer was. So once he got them, he knew he was correct. Okay, so he knew that he was correct. Now, Heisenberg thought he knew what the correct eigenvalues were for uh, rotational motion of molecules. Here he was incorrect, but he actually worked out a solution of his matrix mechanics to give what he thought was the right answer there. Turns out it is the wrong answer. And people actually don't tend to mention this so much. There was another problem that Heisenberg solved that he solved incorrectly with matrix mechanics. Um, and so, there's some interesting side stories in this full story as well. Any other thoughts that people have on this? I mean, what is your opinion? Do you think it's cool? Do you like it? Are you like, eh? I could wait until someone's willing to speak aside from Zach. If you're trying to speak, Marco, you're muted.
Oh, I just say I don't understand the details well enough to say one way or the other.
No, I'm just like thinking. So we are starting from the frequencies of the spectra from the hydrogen, and from there you can postulate these things in quantum mechanics. But are there like in wave mechanics they're dealing with this problem of like, I don't know, like particle in a box and something like that. So I'm just thinking like this doesn't apply to those like 1D problems or anything like that.
Of course it does. It's just we don't solve those problems this way.
Yeah, but like, I mean, they had a specific experiment from which they extracted the frequencies.
No. You're missing. Let me repeat. You're missing you're missing the idea behind this. So the idea behind this is that in quantum, what Spectra told them was that quantum mechanical objects that are observable depend on energy differences. That's the only thing you need to take away from it. It's not like Heisenberg went in and took the spectrum from hydrogen and somehow plugged it into his theory. He didn't even try to solve hydrogen because he couldn't figure out how to do it. Okay. All that is needed is the recognition that unlike what you have in periodic motion, so think about harmonic oscillator, that's periodic motion. In classical mechanics, periodic motion is described by a Fourier series. And so the frequencies that enter into a classical mechanics description are harmonics. But they knew from spectra harmonics were not the important thing. They don't appear in the spectra. Instead, energy differences appear. So somehow in quantum mechanics, there's a transition from in the classical limit where harmonics are important to energy differences being important. So now you have a question in front of you. Energy differences are important. How do I construct an object that depends on energy differences? Because I need to have something like that to describe quantum mechanics. Okay, how do I construct such an object? So I believe the simplest thing that you can construct that does not change the time dependence when you look at more complicated objects like q squared and q to the fourth and so forth is the matrix that Heisenberg postulated.
Okay, does it I mean, the numbers in his matrix, do they have some like for the momentum and for the position, do they have some like physical interpretation of what do
They're
they
exactly
mean?
what you know. They're exactly what you know. They are the position operator expressed as a matrix in between energy eigenstates. The n and the m are energy eigenstates. Q is an operator. I can look at the matrix of Q. In fact, in most classes, you calculate this Q matrix for the harmonic oscillator because it just has the two off-diagonal elements, and you often calculate P as well. It's a very common exercise in a quantum mechanics class to calculate the matrix of P and Q. And once you have the matrix of P and Q, you can actually calculate the matrix of P squared and Q squared as well. And you could even take them and add them together and show that the Hamiltonian comes out to be diagonal. This is done. There are a number of people who do this. If you look at Dirac's book, this is how he solves for hydrogen. He constructs the matrices of P and Q, he squares them, adds them together, shows that it's diagonal. It's a matrix. This is the matrix mechanics way of solving things. So it's the thing that you already know. It's just you never thought about it in this context. And the e to the I omega mn times t, that's exactly what comes out if the energy eigenstates you're working with are time dependent and you're calculating these things as a function of time. So Q of t matrix is exactly the Heisenberg matrix. Is that clear? Do you see that?
Okay, I mean, just like I was thinking, because he invented this, that maybe his initial interpretation was different than what we are.
Well, of course, he knew nothing about. So you have to keep in mind, what did he know? He knew nothing about states. He knew nothing about operators. Those came later. All he knew about was the matrix. So from his perspective, he just wanted to make sure he had an object that had this time dependence. And he wasn't really sure what to do with the rest of the matrix, but he found by clever logical arguments, he could find the spectra of a harmonic oscillator. Okay, so that's pretty cool. And in fact, he corrected the spectra from what people thought the spectra of harmonic oscillator was. Everyone had it wrong. He corrected it. Because everyone thought it was h bar omega times n. And he showed, no, it's h bar omega times n plus a half. So yes, I don't know whether he had some crazy theory for what to do with the Q and the P. I don't know. Okay, or what it meant. But that came very quickly. So I don't know whether it was like Schrodinger's fourth paper or fifth paper. Schrodinger wrote 6 papers in 1926. First paper was hydrogen. Second paper was some crazy thing about a relationship to optics. And then he solved, I think, harmonic oscillator and some other problems in that paper. And then he just started solving other things like hydrogen in a field and some other problem stuff. Total of 6 papers. One of them showed how if you calculate the matrix element using his wave functions, you get the Heisenberg matrices. And that connected everything. And then you can understand how these things worked. So, in order to follow this, you have to allow yourself for some moment of time. It doesn't have to be for a very long period of time, but for some moment of time, you have to allow yourself to be comfortable in the abstraction that I know the Q and the P matrices are important, but I don't know exactly what I need to use them for, aside from the way that we use them to determine what the commutator of Q with P is and how to find the spectrum of hydrogen. I'm sorry, of harmonic oscillator. And then only as you then develop additional postulates do you then understand where they came from. Because for me, what I really like about this is, for me, the most important thing about quantum mechanics is the fact that commutator of Q with P is IH bar. I mean, you can essentially get 13.6 EV for hydrogen just from the commutator. It takes some work, but that commutator has in it the ground state of hydrogen is minus 13.6 EV. Okay, so it all comes from the commutator. Everything that you want to know about quantum mechanics comes from the commutator. Because of that, we should not postulate the commutator. We should find a way of deriving the commutator. It's because everything comes from that. So we should have a way of deriving the commutator. Let's reserve our postulates for things that allow us to derive the commutator. This is my perspective. And I think I have found a way to do that. That's this way. Because I've never been happy. I don't like Dirac saying the way to quantize a system is take its Poisson bracket, convert it to a commutator, and say it's equal to IH bar. I mean, where the heck does that come from? It's like total craziness. We can derive it. Let's derive it. So yeah, we have to give up something when we derive it. So what we give up is we can no longer derive the Ehrenfest theorem. We make the Ehrenfest theorem a postulate and then use that to derive canonical commutation. For me, that makes much more logical sense. You look like you want to say something, Marco, but
No, I have nothing to. It's just this is like it's like maybe it's hard because you learn this as a postulate and then you're like I'm not sure that I understand. Like, okay, now we're trying to derive something which when I was learning quantum mechanics was like just they mention it as like something to begin with, to start with. So
right. So in quantum mechanics, the postulates really come out of thin air. Okay. And it's a little bit weird that, I mean, I think most people are to some extent uncomfortable with the postulates, but they're sort of pressured into just accept it. We all do. This is the way it works. Usually the comment is, why should I believe these postulates? Because when we calculate results from experiment, they agree to experiment better than any other theory that's been tested. So the postulates somehow are right. And eventually we get worn down and we just accept that. And I bet if you think back to how you felt when you first saw this, you were probably troubled by the postulates, but you got beaten down to stop asking why. Okay. I know for myself, that's how I felt. All right. Now, eventually I became comfortable with it. So now when you try to tell me, oh, I want to tinker with the postulates, it's like, well, but wait a second. I finally got to the point where I'm not bothered by them anymore. Now you want to stir it up again. I don't want that. So there's often resistance afterwards, after you've accepted something. There's resistance to change because that means you have to go through this procedure of becoming comfortable with it and accepting it again. But again, just think carefully about how this works. It seems to me to be a very reasonable way to proceed. Spectra tell me I should be working with something that depends on energy differences. The matrices are the most reasonable thing that depend on energy differences. Correspondence principle tells me I should work with the same equations of motion for these objects, even if I don't know exactly what I'm supposed to do with these objects. The fact that the Hamiltonian is time independent means it must be diagonal in this basis. And the fact that, and the only thing that takes a little bit of a leap of faith is the fact that the canonical commutation relation should be independent of the Hamiltonian, although that's not an unreasonable thing to request. And then everything follows from that. I think those are much more reasonable postulates because they're based on experimental observation from the spectra. They're based on the fact that we know quantum mechanics has to go to classical mechanics. And they're based on this reasonableness that this commutator should not depend on the details of the Hamiltonian. That's basically it. Everything else just kind of follows from this.
So what you just described is how he derived it in the paper?
No, it is not. This is my and Jason and Leanne's modernization of the right way to thinking about the postulates. So the way that he worked was they believed the Sommerfeld Bohr quantization condition was essentially correct. But they knew there was something that was not quite right about it. So they wanted to, they called it sharpen the quantum condition. Okay. They wanted to get it into a point where they can revise it so that it's in essentially the same spirit,
well,
but slightly different.
I'm still going to E&M, so can we do this and then
I can have to mute Jason. So what he did was he tried to differentiate the Bohr-Sommerfeld quantization condition with respect to n. Now this brings in problems because n is an integer. So Born, a year before, Born had written a paper where he wanted to do the same thing. And what he did was he just took the finite difference. You take the result for n plus 1 and subtract the result from n, and that's the derivative with respect to n. So if you write out the integral for the quantization condition, and you take a derivative of the integral, and you take a derivative of what the quantization condition is equal to, you find that it is equal, you get that the diagonal matrix element Q with P is equal to IH bar. You learn nothing about the off-diagonal matrix elements, and Heisenberg didn't know anything about the off-diagonals, but you get that all of them are proportional to the identity. But you see his way of doing it assumes canonical commutation is correct. I'm sorry, assumes Bohr-Sommerfeld quantization condition is correct. Or kind of correct, but we shouldn't do it in the integral form, we should do it in the differential form. Okay? That's what he assumed, that's how he did the derivation. But that would not be a good way of making a postulate-based quantum mechanics. Because again, your question would be, well, where does Bohr-Sommerfeld come from? Why should I be doing that? Okay? So that's why the historical way of doing it doesn't really bring in anything new. But if you look at it in this different way, which is really just a slight change of the way in which it's done, it now brings in an interesting new way of thinking about how you should motivate quantum mechanics and how quantum mechanics works. Does that make sense?
Yeah, okay, yeah.
I mean, I don't want to bully you into this. Sometimes people just decide after a while it's better off not arguing anymore because I'm going to just get bullied into it. You know, I'm not trying to do that.
No, I mean, it's not
just
wrong. It's like we know what the solution is. It's just like
right. But I mean, the key is that you know, it's sort of the way that I like to describe it is the Bohr-Sommerfeld quantization correction is correct for the integer part, but is not correct for a constant correction to that. And when I take the derivative of it in this Born way of taking the difference of the results for two integers, the constant piece drops out. And that's how you correct what is sort of right into being right. So that in many respects, the differential form of the Bohr-Sommerfeld quantization condition is actually the correct condition. And that does become the canonical commutation relation. But you only know that with 20/20 hindsight. You only know that after you've solved the things. So it's in my opinion a very poor postulate to use as a postulate for quantum mechanics. Essentially, what you're doing is you're postulating commutator of Q with P as IH bar. And I think it's much more interesting to have a way to really derive commutator of Q with P as IH bar. And that requires some different postulates. But for me, I think it's really much cooler to have some set of postulates that are very reasonable and are not so contrary to things I already know, and use them to derive the canonical commutation relation. So that's the idea behind it. Ryan, Oleg, Jeremy, you guys have any thoughts or?
I'm not sure I completely followed, but I do think it's definitely cool. And I think that it is more natural probably to start with Ehrenfest as the postulate and then derive the commutator than the other way around.
Yeah. I mean, if you look at the derivation of Ehrenfest, it has the commutation relation is like intimately embedded in the derivation. So I don't think there's any way of deriving Ehrenfest without already having the commutation relation. So it's kind of hopeless, because what you do is you use the Heisenberg equation of motion. Commutator of H with P is equal to that's P dot, and then you actually calculate the commutator of H with P, but you can't calculate that without knowing the commutator of P with Q. Okay, but if you know what the commutator of P with Q is, then of course you get the right equation of motion. So yeah, so it's sort of one or the other. And the current way of doing it, where you postulate canonical commutation relation and derive Ehrenfest, does seem backwards to me as well. It really seems like the natural thing is to say, let's just preserve the classical equations of motion because we know somehow they should be correct. Now, I mean, it could be that there's some quantum correction to the classical equations of motion, and that would be something that we would have to include, but it seems to be that that's not the case. There isn't a classical correction to the quantum equations of motion, so everything turns out to be nice. Oleg, do you have any thoughts? Or Jeremy?
Yeah, I can say something real quick. I think I am in a similar camp to Ryan. I find it a lot more satisfying to derive the commutator than to take that as a postulate. I definitely think that, like when you mentioned going back to sort of the mindset when you first learned it, I definitely had sort of a deja vu moment there, and definitely find that really satisfying. So yeah, but I'm not 100% sure if I've got all the details down at this point on it.
Yeah, I mean, it takes a little bit of time. Mainly, as I mentioned this to many people, it's more just becoming comfortable with a different way of looking at things than it being hard or difficult to understand. And if you can't even remember how it works, you certainly are not yet able to be comfortable with it. So there is a process that you have to go through to get there. But yeah, I mean, I do think in many respects this is a more natural way. And the only thing then that is really a big leap, and it is a big leap, is to say that the matrices are sort of the hint that there's actually this abstract space that we have to do all of our quantum mechanics in, and we have to introduce abstract state vectors and things like that. If you're a mathematician, I don't think that's so difficult because mathematicians know that matrices are just the representation of operators in a vector space. So it's not that big of a leap to move from matrices to operators in a vector space. Okay, but for someone who hasn't been trained to think abstractly, that's a big leap. Matrices seem much more concrete. Abstract operators are much more abstract, harder to follow, and so forth. But it's very difficult to do anything in quantum mechanics if you're not willing to start working with operators at some point. So that's kind of a requirement. So in any case, that's what I wanted to share. Thanks for your opinions. I don't know if anyone else has anything more that they'd like to say. I think it's also really nice to see the logic behind how this discovery worked. Because in many respects, I don't think it is so different from something that you or I might not be able to figure out on our own as well. Again, as I said, once you recognize that the energy differences are the important thing, you're almost forced into matrices. And once you have that idea, the rest, I think, follows pretty straightforwardly. You might have some trial and error to figure it out, but I think it follows pretty straightforwardly after that. The key insight is the matrix part itself. So